take a look at some of these other weak bases in this table right here. So we call all of these amines. And I do want you to know that term, and I want you to recognize what an amine is. So an amine is something that has this base NH3 structure. So you can see here the structure of ammonia, NH3, right? Recall that it has this nice tetrahedral structure with this open lone pair, okay? And so that's what ends up forming a bond. Let me draw that again. So that's what ends up forming the bond to hydrogen when this undergoes its base reaction, its proton accepting reaction. So here's all of our Lewis structures, right? So you can see now this open lone pair is primed for accepting. So the electrons are really what grab the protons, right? And now the electrons in this bond get pushed over to the oxygen. And so now what we have left, we've created now a new hydrogen to nitrogen bond. And because we're adding a positive hydrogen, this whole thing has to be positively charged, right? And then now what we're left with is an OH. And you can see we had two lone pairs on there before. But now this bond to hydrogen also becomes a lone pair. And because we've tacked that extra lone pair on, this gives it the negative charge. So that's how we recognize these amine formulas when we see this either NH3 or in the case of, let's look at the next simple example, methylamine. So you can see in methylamine, it's nearly the same as ammonia, but instead of a hydrogen right there, it's a CH3 group. So I'll write this in a more succinct way. So that's like an H2N, which would be this chunk of the molecule, bonded to a CH3. So that CH3 is what we call methyl. And this NH2, that makes the amine group, so methylamine. And you can see that it's got that lone pair right there. So when methylamine, you can see here it is CH3 NH2. So I realized, I wrote that like backwards than what it shows here, but it's okay, right? It's just showing that it's the carbon and the nitrogen that are bonded to each other, right? As we can see right here. So when that methylamine goes through this reaction, look, it's the same generic formula that we showed before. B becomes BH plus, right? So we can see the methylamine, CH3 NH2, grabs a proton from water and becomes now CH3 NH3 plus, okay? So check it out. Here's dimethylamine. And dimethylamine has that nitrogen lone pair. It has the one hydrogen. But now look, see how it says CH3 two times? So that means it has two CH3 groups, okay? And so when dimethylamine undergoes its weak base reaction, it was CH3 2NH. Now it becomes CH3 2NH2 plus. So once again, following this same generic idea. Okay. And then now you can see we have some more complicated things on there, such as aniline or pyridine. So for you men out there, pyridine is actually known to cause irreversible damage to the male reproductive system. So there's a lot of male chemists out there who are like scared to death of working with pyridine, me being one of them. Although I've already had a child, and so we're past that. But all the same, when I was a student, I remember like I was scared to death of pyridine when my chemistry teacher told me that pyridine can wreak havoc on the male reproductive system. So anyways, there's some extra information for you. Okay, so now these structures are more complicated, and I don't expect you to have the structures memorized as long as you can still go through the generic reactions. So you can see pyridine doesn't have any of these hydrogens at all. Instead, it has this ring structure. And I'll just give you a quick reminder. When we have that ring structure right there, that means that there are actually like resonance structure double bonds. Okay, so each one of those points here, I should actually just draw it like out completely. Okay, so that's a bond to a carbon, a bond to a carbon, a bond to a carbon, and so on. So it makes this nice little hexagonal shape. So you can see that pyridine has 5 carbons. There they are, 1, 2, 3, 4, 5. And there's 5 hydrogens. So each carbon has a hydrogen bonded to it. That makes this lovely looking ring structure. But now you'll notice that it is deficient in electrons, right? So carbon wants the octet rule. So it has 2, 4, 6. Carbon needs an extra bond right there. So there it is. So there's a double bond to the carbon and nitrogen. And so now this carbon has 2, 4, 6, but it needs another bond. So there's a double bond, okay? So now each of these carbons are okay. And now finally, this needs to be a carbon-carbon double bond. So that's what that circle around the ring represents, that there's these rotating double bonds. And you can see similarly, aniline also has that ring structure, which I'll just abbreviate like so. But now the nitrogen is up here, 2 hydrogens, and then there's the lone pair. And if we look at how they go through the reactions, right? Pyridine is just C5H5N, but now it becomes C5H5NH+, just like our B goes to BH+, and same with aniline, right? It was an NH2 at the end there, now that becomes an NH3+. Okay, so what is it about these structures that make them weak or strong? And I'll also remind you, we can rank these in terms of their strength. And what we actually see is dimethylamine is the strongest out of all of these. So we'll say rank, okay? And you can see methylamine is in a close second, followed by ammonia, and then pyridine, and then aniline. So what is going on with these structures? Okay, well, if we look at, let's pick on, so dimethylamine, there it is, I drew it, okay? And so we remember now, it's not so much about it having a weak bond, but what it's really all about is how well can it attract a positive hydrogen. So that's what it's really all about, because it's trying to attract this positively charged hydrogen to form a bond there. So as it turns out, the more electron density, so the more electrons there are in the vicinity of that nitrogen, the stronger of a base it is. So let's compare the series ammonia to methylamine to dimethylamine. So we remember that ammonia is just all hydrogens. We also remember hydrogen only has one, so I had that backwards, 1 electron, right? Each hydrogen only has 1 single electron. So if we think about how many electrons there are in the vicinity of this nitrogen, it's not very many in comparison to the methylamine, because this methylamine, it's got 2 hydrogens, but now this carbon that it's directly bonded to has a lot more electrons that it can donate to the nitrogen. And then similarly, the dimethylamine, we get rid of 1 more hydrogen, and now it's bonded to 2 carbons. So you can see that means the dimethylamine, because it has the most electron density surrounding the nitrogen, it is more likely to attract a hydrogen to those lone pairs. And so that's what gives it the biggest Kb. So in other words, it produces the most amount of BH plus and the most amount of hydroxide. So it reacts to the right more than any of the others. And you can see methylamine is in a close second place because it has two hydrogens, but it still has a lot of electron density from that carbon. But now if we look at, for example, these two ring structures, the aniline and the pyridine. So all of the electron density, so we'll say electrons, are getting sucked down into the ring. So because that ring structure has those double bonds, that's where those electrons want to funnel down into to create the stabilized resonance structure. So electrons are being sucked away from this nitrogen. So that means it can't attract hydrogens as much. Okay, so we call this being delocalized electrons. So the electrons are being delocalized away from the nitrogen. Okay, and so that's what gives us the degree of strength amongst the weak bases.